In this video, we will explore retry and backoff strategies for handling transient failures in distributed systems. A distributed system is a system in which components located on networked computers communicate and coordinate their actions by passing messages. This is essential for building robust and reliable applications in today's complex environments. Let us understand what are transient failures. Transient failures are temporary issues that resolve themselves without any manual intervention. Think of them as hiccups in your system. These are not permanent problems, but rather short-lived disruptions. Here are a few common examples. The first one is network timeouts. Brief network congestion can cause delays in request processing. The second one is resource exhaustion, where there are temporary spikes in central processing unit, or CPU, or memory usage. The third is service overload, which means high traffic can cause temporary unavailability of the services. Let's discuss the importance of retry strategies. Retry strategies are important because they improve system resilience. By automatically retrying failed operations, the system can withstand temporary disruptions. It provides a better user experience. Users are less likely to experience interruptions or errors, leading to higher satisfaction. Finally, it provides automatic recovery, where the system can automatically recover from transient failures without manual intervention. Now let's look at the risks without a strategy. The first risk is cascading failures, where one failure can trigger others, leading to widespread outages. The second risk is system overload. Retrying without a strategy can overwhelm the system, making things worse. The third one is poor reliability, where the system becomes unreliable and unpredictable, eroding trust. Here is a basic retry pattern implementation with a code snippet. Let us define a function named retry_request which takes the URL and maximum attempts as input. The maximum attempts is set to 3. Then we iterate through the attempts. Within the try block, we make a GET request to the URL and return the response. If any exception occurs, the code goes into the except block and checks if it has reached the maximum attempts -1. If it is true, it will raise the exception. Otherwise, it continues to the next attempt. Here are a few key concepts. The first one is fixed retry count, which means the number of retries is predetermined. The second one is immediate retry, which means retries happen immediately after failure. The third is exception handling, where try and except blocks are used to manage failures. The fourth one is final failure propagation, where the exception is raised if all retries fail. Let's dive into the exponential backoff strategy. This strategy introduces increasing delays between retries to avoid overwhelming the system. Here is the code. First, we import time and random modules. Then we define a function named exponential_backoff, which takes attempt as input. The delay is calculated as 2 raised to the power of the attempt number, plus a random number between 0 and 1, which is called a jitter. Then the program goes to sleep for that particular delay time. Then that delay is returned. Then we define another function named retry with backoff, which takes a function and maximum attempts, the default being 5. Then we iterate through the attempts. Within the try block, we return the execution of the function. If any exception occurs, the code goes into the except block and checks if the attempt is less than the maximum attempts -1. If it is true, we call the exponential backoff function with the attempt number as an argument. Here is the backoff formula. Delay equals 2 raised to the power of n plus jitter, where n is the attempt number. For example, for attempt 1, the delay will be approximately 2 seconds. For attempt 2, it will be approximately 4 seconds. For attempt 3, it will be approximately 8 seconds. For attempt 4, it will be approximately 16 seconds. Now let's see why jitter is important and what are the advanced strategies. Let's understand the problems first. Synchronized retries create a thundering herd effect, overwhelming the server. So, the solution is to add randomness to spread out retry attempts. Here is the formula. Delay equals base delay plus random between 0 and jitter range. Here are a few advanced patterns. The first one is linear back-off, which has a fixed increment between retries and is predictable. The second one is circuit breaker, which stops retries when the failure rate is high. Protects the resources. The third one is adaptive retry, which adjusts the strategy based on the system state. It is intelligent. Let's discuss the best practices to follow. First, set the maximum retry limits. Second, monitor retry metrics. Third, log retry attempts. Fourth, use appropriate timeouts. Fifth, implement jitter. Now let's see what not to do. First, do not retry non-transient failures. Second, do not use infinite retry loops. Third, do not ignore retry amplification. Fourth, do not retry immediately without a back-off. Fifth, do not retry authentication failures. Here are a few important things to remember. First, choose the right strategy for your use case. Second, monitor and measure retry effectiveness. Third, exponential back-off with jitter is often optimal. Fourth, implement circuit breakers for protection. Fifth, test your retry logic thoroughly. So, retry strategies are essential for building resilient distributed systems. So, build for failure and design for recovery. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.